Today we're going to be focusing specifically on the effect of changing the intensity on the photoelectric effect and the values that we looked at in a previous lesson. I am going to be using a bit of a simplification, and we're going to talk more about unraveling that simplification a little bit in a future lesson. Now, the first thing that we can be exploring is this voltage and current graph. And we explored this a little bit last time when we had our simulation. Here's the PhET simulation that we previously were having a play with. We could change things such as the intensity, we could change the wavelength, which changed the frequency because they have a reciprocal relationship, and we could also change this metal surface and the voltage across these two plates. That's the voltage across this voltage source here. Now, let's leave this as sodium. And what we want to do, like we saw in the graph in the notes that we just saw, we want to explore the relationship between the current, aka the photocurrent, and the voltage of this source here. So let's turn our lamp on, let's put that to 100% intensity, and we've noticed we've got some electrons coming out. As we spoke about last lesson, an important feature of this simulation, which nicely replicates real life, is that some of the electrons are traveling faster than others. That's not a bug of the simulation. The simulation's pretty good. It is a feature. The electrons have varying amounts of energy because some were more tightly bound to that metal, in this case sodium, than others. So it was more difficult to liberate them from the metal surface, therefore they have less leftover kinetic energy. And we talked about the fact that changing this voltage allowed us to explore some features of this graph. So let's, as I said, we look specifically at current and battery voltage. So here we've got the graph, and I'll zoom in a little bit here so we can see what's going on. Now, let's start by making this plate more positive. The simulation is slightly oversimplified, but let's see what effect this has on the current. We're going to be increasing the voltage, so we're going to have values, we're currently at 0, we're going to go from 2 all the way to 8, and we're going to see what impact that has on this current measurement here. Is it going to go down? Is it going to go up? What's going to happen? So increasing this, we can see we've got more positive charges on this side because we've increased the voltage between the plates. And I notice the current is sort of flatlining. Now, you might be saying, why isn't the current going up? These electrons are traveling through the gap more quickly. How long it takes them to traverse this particular gap doesn't impact the total rate of flow within this external circuit. So the rate of flow of electrons per unit time. So they could crawl across the gap, they could sprint across the gap, but what matters is the number of electrons that are being collected at the electrode per unit time. And it doesn't matter how quickly they traversed it. The number is the main thing that's going on here. I'll talk more about that in class. It's a bit of a nuanced point. But the point is, we can see the current is unchanged. We can also see the current in this little ammeter thing here. It's stuck at 0.141 amps. So that's a really important feature of our graphs. Let's go back to our notes and note down what we noticed. So as we increased the positive charges on this plate here, we did that by increasing this voltage as time went on. We noticed our graph was stuck at a particular maximum value here. That's very important. We can't increase the photocurrent by making this plate more positive. Let's go back and look at the simulation, but now we're going to start making this plate more negative, and let's see what impact that has. Now, like we looked at last time, when we started going negative, we noticed, are we going to have one happen? Oh, we've got one that's just close to the plate. Oh, that one made it. Is this one going to make it? No. So once we start making this plate negatively charged, some of those less energetic electrons are being repelled from that plate. And remember, we talked about the fact that all of their kinetic energy that they left that sodium plate with was converted to electric potential energy, meaning they had no kinetic energy, and just like a ball thrown up in the air will come back down, these electrons fall back towards that sodium plate. Now that's not the least energetic electrons, but some are still able to make it. So we've noticed on our graph here, our current has begun to reduce, but it's not gone exactly to zero because those electrons have varying energies. Let's make this even more negative. Oh, unfortunately, there's difficulty for nuance with me trying to use this slider. We'll go a little more than we were before. There we are. Oh, best I've currently got. That's a current joke. So we can see that some of the electrons, even more than last time, are unable to make it. Previously, we were at about negative 0.2, I believe. Now we're at 0.4. If we continue to make this negative, we'll reach a particular point. I'll see if I can type in a nicer value. Let's go 0.6 negatively. Oh yes, if we look at our current graph, current voltage graph, we can see some electrons are still going to make it. Oh, there was one. So let's see if we can make this slightly more nuanced. Let's put in a negative 0.8. Oh, still had a couple, but they may have been due to the previous situation. Let's have a little look-see. Oh, we've got a few really energetic ones. They've just not made it. So this value here, we referred to this as, it's got a few names. You could call it the stopping voltage, the cutoff voltage, stopping potential, cutoff potential. We called it V0 when we were applying notation to it. So that's important. This side of the graph, we had a relatively steady decrease in the current. So let's go back to our notes. So at the maximum value that we had previously, we had a downwards trend here. And this value on this graph, that was our value of V0, the stopping voltage. So you can imagine if we put these two graphs together, we'd have something that looked like this. And we'll talk more about that in a moment. So, important things to notice. We had, at this point here, we had the less energetic electrons are unable to reach collector electrode. And that continued. You know, in the midpoint here, we had the medium level electrons started not being able to make it until we got here. Even the most energetic electrons don't make it. And that is the very important value of V0. And not that we really draw this section of graph here, but if we continue to make this even more and more negative, look at the struggle of the electrons here. So we don't really care about these because we know at that one that we previously had, that was about negative 0.8 or something like that. That was the first voltage that stopped those electrons. We know if we made this plate even more negative, those electrons are going to struggle even more. Now, in actual fact, the graph is a little more nuanced than that. And I'm going to be honest, in the exam, I haven't seen many more graphs that aren't that simplification from before. You'll notice, for example, this graph, it takes a moment to get to that maximum current here. I'm just going to write I maximum. The reason being that positive plate can encourage any electrons that may previously, if this was like our sodium plate from before, and this was our collector electrode, there may have been some electrons that flew off in this direction that didn't make it to this collector electrode here. So by making this one even more positive, we can really encourage those electrons to go in that direction. So that's why you may see some graphs with a bit of a curve here rather than going straight to that maximum. As I said, in the exam, it tends to use the simplification that it goes straight to the maximum, but be comfortable with the fact that you may see a bit more of a curve here. You might also see a graph that has a little bit of a curve here. Again, simplification, you're very likely to see it as linear, but you could see a curve. Regardless of the situation, you can read V0 on this graph because that is the situation where if this was our current, and that might be in amps or milliamps, it depends, and this will be our voltage, likely volts, we're able to read the value of V0. Perhaps you could also read the value of Imax, which we also put that on before. But the most common thing you'll need this for is V0. So it's a relatively simple graph in terms of the data that we can collect from it. But knowing that stopping voltage is incredibly powerful. Now, here's an example of a past exam question. I'm sorry, I forgot to write the year number on this one. So this shows you the kind of thing that you'll experience. Here we have yet another diagram of the photoelectric effect. We have the metal where light is shining upon it. We have our collector electrode, and we have our other standard things, our variable voltage that allows us to do what we literally just did. We can see what kind of reverse voltage will start stopping those electrons until we get to that voltage, the first voltage, that stops all of the electrons, even the most energetic. And we have an ammeter and voltmeter to tell us information about that. So let's read the question. A student carries out an experiment to investigate the photoelectric effect. She shines monochromatic light onto a metal plate inside a sealed glass chamber as shown in figure 2. So this would have a sealed glass chamber. We don't want those electrons colliding with like oxygen and stuff like that. I'm so sorry about the formatting of this question. I don't know why it's ended up over here. We want to know what is the stopping voltage and maximum kinetic energy, so stopping voltage and maximum kinetic energy in electron volts of the electrons ejected from plate P. Okay, so stopping voltage is here. Now, an important thing, a critically important thing you need to be aware of is we quote stopping voltages as a positive value. We don't quote them as a negative value. That negative was just saying it was a reverse voltage that is applied, but we just care about what size reverse voltage, so we just quote it as a positive. We saw last lesson that the maximum kinetic energy of the electrons has the same numerical value as the stopping voltage, but instead of it being quoted in volts, it's quoted in electron volts. And we looked at the reason for that. It had to do with the work done of an electron crossing the gap. So this question, quite nice, is literally one value to quote from the graph, and we had to take the magnitude of that value. So we're going to now focus on the main purpose of this lesson, changing the intensity of light. We're getting into some territory which there's been some simplifications used for this over the years, which previously was very happily followed by the exams that we experience, but particularly in 2024, they expected an increased level of depth with this. I'm going to talk about that increased level of depth in a future class. So we are going to be working with this simplification for now, with extra nuance to come in future. So bear with me while you can. First off, we need to talk about what intensity is related to. That can be really thought of, at least for now, to be to do with the brightness of the light. And the simplification that has been allowed in the past is say, well, that's going to be proportional to the rate of flow of photons. And the rate of flow of photons is just saying how many photons, not hashtag photons, but how many photons we have per unit time. So if we just consider intensity for now as the rate of flow of photons, the number of photons that we have coming out of our light source per unit time, we can look at a particular wavelength of light and see, well, let's get that back in. We can look at a particular wavelength of light and we can see how will having more photons of that light impact our current voltage graph that we looked at previously. Again, that current could be in something as large as amps, but you could see milliamps or microamps, so just be aware of that. Well, if we take intensity to be the brightness, and that's the rate of flow of electrons, an increased intensity means we're going to have a larger number of photons. And again, you might have seen straight line graphs here rather than these curves. So increased intensity, if we have a larger rate of photon flow, a larger rate of number of photons per unit time, more photons means we're going to have more electrons able to absorb those photons. The electrons can only absorb one photon each, so if more photons are available, more electrons can absorb them, and provided we're at one of these positive voltages here, we're not trying to repel those electrons, we're just collecting them, we're going to have a greater flow of current. So an increased flow of photons per time means we can have more electrons that can absorb those photons. And more electrons moving through our circuit means, these these arrows are indicating the direction of our logic here. They're not saying something's decreasing. So more electrons able to absorb those photons means that we have a greater current, and that's these larger values of the current we're measuring here. If the initial intensity was somewhere in between and we were to decrease that intensity, the opposite thing would happen. We would have a lower number of photons per unit time if we're looking at this. We would have fewer electrons able to absorb those photons, and we would have a lower current measured. So, if brightness is the rate of flow of photons, that's the flow of the logic. How many photons are available? An electron can absorb each one of those photons. If those electrons have absorbed the photons, they're moving to the collector electrode, so that means we're going to have a larger current. So that's really helpful to know. This is continuing from the previous question, saying if the intensity of light is doubled, what effect does this have on the stopping voltage? Now that leads us to the second part of this graph. All of these, it could have been linear lines coming to this point, or it could have been these curved lines, but all of these lines here are coming to that same stopping voltage, which we would quote as V0. The reason that doesn't change, the stopping voltage, or the reverse voltage required to stop even the most energetic electrons, for a fixed wavelength, and therefore fixed frequency, the energy that each of these photons is imparting is the same. So each of these electrons has the same energy available. So it's not going to change the reverse voltage needed to stop those electrons traversing that gap. So let's put something like the max kinetic energy electrons can have is unchanged due to E photon remaining the same. Therefore, our stopping voltage is unchanged. So looking at that continuation of the past exam question, what effect does this have on the stopping voltage? None. Let's explain that. So let's make a note of the fact that intensity does not change the energy of individual photons. And then in brackets, I'm going to say it just means there's more of them. If specifically intensity was doubled. Oh, let's actually be a bit more specific. Rather than saying it's more of them, there are 2 times as many of them. There, that's a bit more specific. So what effect does this have on the stopping voltage? Intensity does not change the energy of individual photons, as Ke max in EV equals V0 in volts. Electrons having same Ke max leads to V0 same. And they have the same Ke max because remember, Ke max was equal to the energy the photon supplies minus phi. Okay, our claim is that we do claim evidence reasoning when we're explaining. Our claim is that there is no impact on the stopping voltage. Our evidence and reasoning, well, we talked about how intensity doesn't have anything to do with, intensity does not change the energy. So intensity doesn't have anything to do with the energy of the photons. And we've also mentioned if the energy is the same, the stopping voltage is the same. And there's all sort of points of reasoning. Our evidence had to do with the Ke max and the fact that Ke max is related to V0. So it's quite a few sophisticated concepts put together there. Part C is asking us, sketch the shape of the graph if the intensity of light was decreased. We need to read that carefully because part A is talking about the intensity doubling. Part C is asking if it decreased. Going back to this previous graph that we had, if the intensity of light decreased, we don't need to put a particular value here. Let's just put a smaller maximum photocurrent. If the intensity of light decreased, that means the number of photons per unit time decreases. Therefore, the number of electrons emitted decreases. Therefore, the current decreases. But like we mentioned in the previous question, we're still going to have this same stopping voltage. So we're going to have a graph that looks something like that. Okay, this was looking at how the intensity of light impacts the current voltage graph. There are quite a few sophisticated concepts here. If you have questions about this, please let me know next lesson.